has to do with not any particular edge case, but the fact that there are so many things that are potentially edge cases depending on how you build your system. Let me give you a concrete approach to explain why these numbers can't add up and why they're such a problem. Let's do two examples for a situation in which you're going to do 1 billion miles of drive fix drives. You're going to drive around, you're going to find problems, SOTIF triggering events, for example, things that your system doesn't do. You're going to fix the problem, you're going to keep driving, and you're going to do that for 1 billion miles. Now, the good news is after 1 billion miles, you should have seen most things that are going to happen, or at least intuitively after 1 billion miles, you should have seen pretty much everything. But that intuition is based on a Gaussian distribution that has very, very small tails. And it might not be true, and in fact, it's probably not true of the real world. But let's do a numeric example to illustrate the point. Let's assume that you have unsafe surprises every 1 million miles. So your vehicle has gotten so good that something weird happens that your system does not know how to deal with only once every 1 million miles. The question is, how many surprises are there that are out there? Well, for example 1, let's assume there's only 100 surprises or categories of surprises you've never seen before the first 1 million miles. Each one of them is 100 million miles per surprise. So that means each one of these you'll see 10 times during testing. Revisiting that math, it's 100 million miles between each type of surprise, but there are 100 different surprises, so on average, one of them will show up every 1 million miles, usually be a different one every time. Nonetheless, after 1 billion miles, you will have had the chance to, on average, see each of them 10 times, and if you figured that out and fixed it, at the end, you're done, no bugs left, everything's good, and you can now do your brute force campaign to prove you're safe. Well, that's a bit optimistic. Consider this picture. Is this a car or a house? Well, a little bit of both. And if you never trained on something like that, then you may miscategorize it and might do something dangerous when it starts moving at an intersection when you thought it was a house. In fact, if you go to a web search engine and type in a query such as weird road obstacles, you can get sucked into that vortex for hours of looking at all the bizarre things you'll see on the road. For those of you who decide to do the web search, welcome back. Hopefully it's still the same day, but let's continue on with the second example. The second example is still 1 million miles between unsafe surprises. But let's say there are 100,000 surprises, each one of which is exceedingly rare. Each surprise only happens every 100 billion miles. That's almost never. And you might say, well, every 100 billion miles, I'm just not going to worry about it. Well, the catch is that's only half the problem. The other half is there are so many of them that on average, there's still something is arriving every 1 million miles. It's just, for practical purposes, always a different thing. So even if you do 1 billion miles of testing, you're only going to see 1% of the surprise population. And even if you fix everything you've only seen once, those bug fixes don't really give an improvement. You're only going to get 1.01 million miles per surprise instead of being completely fixed. Now, these are hypothetical numbers. I just took 2 points on a spectrum to do examples to explain the issue. The issue is not only how often do you see something unsafe happen that you need to fix, it's also what does the population look like? In other words, if you fix things that are a problem, if it's a huge population of problems, it will take you a long time to make progress. Fixing one problem out of 100,000 basically doesn't do anything at all. One problem out of 100, well, that's worth doing. And the question is, what does the real world look like? And the unfortunate news is the real world probably looks more like example 2 than it does example 1. And that bodes poorly for brute force approaches to find problems and then fix them. You'll basically never get there.